finished the chapter which is the mole concept chapter, okay, where we took almost 6 sessions. So I welcome you today to the 7th session of our JEE chemistry, where we are going to start the next chapter, that is redox reactions. Okay, good afternoon everyone. Let's begin. Hi Likhita. Okay, chalo. So what is redox? So redox technically means the reaction which includes reduction as well as oxidation, right? Redox actually is a joint word formed from oxidation and reduction, and that is why we will see what oxidation is and what reduction is. You can see there's a word oxy in oxidation. So this oxy stands for what? This oxy stands for oxygen. That means in oxidation, we have addition of oxygen. That means if any compound is getting added to the oxygen, then that compound is said to undergo oxidation. In the given example, magnesium is reacting with oxygen to give you MgO. That means your magnesium is undergoing oxidation. Okay, reduction. Now see, oxidation, reduction, both these processes goes hand in hand, but obviously they goes hand in hand, but these reactions are complementary to each other. I would say they are exactly opposite in nature. That means if the addition of oxygen is oxidation, then removal of oxygen has to be reduction. Removal of oxygen has to be reduction. For example, here CuO is there. CuO reaction with the coke, which is carbon, which gives us Cu plus Co. So here Cu has lost an oxygen. So since Cu has lost an oxygen, it is said that Cu has undergone a reduction. Okay. If you look at this reaction from another angle, you will be able to see that carbon has got oxidized here. As we had seen in the earlier definition, any compound which goes with the oxygen is said to be oxidized. Similarly, the carbon here is going with the oxygen. So carbon is getting oxidized and Cu is losing oxygen. That means Cu or copper is getting reduced. So you can clearly see here, this reaction is nothing but the redox reaction. More often than not, you'll always see oxidation accompanied with reduction only. You will not see only either of them is happening. Okay, that's very, very rare. I would not say even a rare, it doesn't happen. It's like if I'm losing something, someone will gain it, right? It's not that I'm losing only and nobody is gaining. No, it's not that. If I'm losing, someone will gain. So it's just like that. That is how oxidation reduction goes hand in hand. Okay, next, removal of hydrogen. Oxidation is here, the terminology of oxygen and hydrogen is opposite for oxidation. So you remember only for oxidation. For reduction, you can reverse it. So as far as oxidation term is concerned, you know that oxy word is there. That means oxygen is getting added. So if the oxygen is getting added, that means hydrogen must be getting removed. The removal of hydrogen is called as oxidation. So here your H2S is reacting with Cl2, right? So H2S is losing hydrogen to chlorine. Sulfur is losing hydrogen to chlorine to make it HCl and sulfur, non-metallic sulfur. So sulfur has got reduced here because it has, sorry, my bad. Sulfur has got oxidized here because it has lost a hydrogen. Similarly, addition of hydrogen. So if the removal of hydrogen is oxidation, then addition of hydrogen has to be reduction. Here sulfur is getting added to hydrogen to give you H2S. So your sulfur has got reduced here. Sulfur has got reduced. Yeah. Next, see, you already know what is the meaning of reduction. Reduction means something getting reduced, or something getting decreased, right? This is quite easy to understand, right? Something getting reduced or something getting decreased. Now, so what is decreasing? Decreasing is positive charge. Positive charge is getting reduced. So whenever you see positive charge getting reduced, that means you can see here Fe plus 3 is going plus 3 to plus 2. This positive charge is getting reduced, and that is why we call this as reduction. So if the reduction is getting positive charge reduced, what must be oxidation? Exactly opposite to it, right? So oxidation must be increase in positive charge. So you can remember for the oxidation that it is the addition of oxygen. So if it is the addition of oxygen, it has to be removal of hydrogen. Make it reverse for the reduction. For the reduction, it is the removal of oxygen and addition of hydrogen. These are the two ways by which you can remember what is oxidation, what is reduction. The third way, if the positive charge is getting decreased, that means reduction. Then what must be oxidation? Increase in positive charge, right? So that is how oxidation and reduction can be classified. Okay, so moving ahead, another oxidation number. You will see very shortly what is oxidation number. For the time being, if the oxidation number decreases, as I told you already, in that case I was using the term called positive charge, but not necessarily it will always be a positive charge. The better way to say is that if the oxidation number is getting decreased, where it is going from plus 7 to plus 2. So obviously decrease means reduction, right? It's a typical English word. For oxidation, oxidation is not typical English word. So for oxidation, remember it for the reduction that something is getting decreased. What is getting decreased? Oxidation number. Then make it reverse for the oxidation. Now oxidation number is getting increased. You can see here tin is going from plus 2 to plus 4. That means tin is getting oxidized. Manganese is going from plus 7 to plus 2 here. That means manganese is getting reduced. And lastly, removal of an electron. Removal of an electron or loss of an electron. Removal of an electron or loss of electron is called as oxidation. So exactly opposite to it, addition of electron or gain of electron has to be reduction. Okay, you can see here Sn or tin is in plus 2. Plus 2, that means it is short of 2 electrons. From there it is going to plus 4. In a plus 4 it is short of 4 electrons. So short of 4 electron is definitely larger than short of 2 electron. That means where it is 4 plus, it has lost 2 electrons. And that is why it is oxidation. Similarly, reduction. Fe plus 3 means your ion is a short of 3 electron. From there, it is gaining 1 electron to becoming a plus 2. In plus 2, it is short of 2 electron. So your ion has gone from short of 3 electron to short of 2 electron. That means your ion has gained 1 electron. That is why it is called as reduction. So these are the 5 ways by which you can identify whether the given reaction or process is oxidation or reduction. Okay, I hope this must have been clear to you. Moving ahead, most important term of this chapter, oxidation number. What is oxidation number? See, oxidation number is a imaginary or apparent charge. You need to call it as imaginary because there is nothing like this. If you write Fe plus 2, this plus 2 is just an indication. This plus 2 indicates that your ion has 2 electrons less than the neutral ion. That is what it indicates. Or even if you have a negative charge, for example, if you have a O2 minus, this 2 minus indicates your oxygen has 2 electrons extra than what it should have as a neutral atom. So this oxidation number is just imaginary apparent charge gain, or I would say indicated by the element's head. It is gained by element when it goes from elemental free state to combined state in molecules. Now, whenever a given atom or element, whenever it is in a combined state, obviously its oxidation state has to be 0. When it goes to the combined state, that means whenever it forms a molecules or a compounds, there is going to be some electronegativity difference. And that is when this oxidation number or oxidation state term comes in. Okay. What are some rules? Rules for governing oxidation number. See, the most important rule which governs the oxidation number thing is the electronegativity. Electronegativity is the most important thing here. The basis of all this rule is the electronegativity of the element, because the electronegativity will tell you whether your atom or element will have a positive charge or negative charge or a no charge. It all depends on electronegativity only. Okay, let's see how. See, fluorine atom. Now, you might know fluorine atom is the most electronegative element in the periodic table. You can also, it also been referred as a king of electronegativity. It is also referred as king of electronegativity. It is having a literally like this. So your fluorine being a most electronegative, it will never lose electron. What I mean by that, whenever it is bonded to any other element, you can never drift the bonding pair of electrons away from the fluorine. In fact, it's either way. Whatever element you take, for example, take a given element E and your fluorine is covalently bonded with this E. This E could be anything, okay? This E could be any element. Take it from hydrogen to the last element. Doesn't matter. What fluorine will do, fluorine will start pulling the electron density away from this element. When that happens, fluorine will acquire a partial negative charge and your E, whatever element it is, will acquire partial positive charge. So that is the case always. That is why fluorine is literally having a crown of a king of electronegativity. So fluorine shows only two oxidation states. One is 0. 0 it is when it is combined with no other element, when it is attached with its own atom. For example, in F2 molecule, one fluorine atom is attached to another fluorine atom. So that means electronegativity difference is 0. It cannot withdraw electron density away from the other fluorine atom. So that is why it is 0. And otherwise, it is always in a minus 1. Basically, 0 is the oxidation state shown by every element. So let's not take it into count whenever we will talk about the oxidation number shown by the given element. So fluorine has -1 in its compounds. Okay, always. By that I mean always. Next is oxygen atom. Now in general, as well as in its oxide, oxygen atom has oxidation number equal to -2. Now -2 is its common oxidation state. Okay, more often than not you will see oxygen showing -2, but yes, there is a quite a variation with the oxygen's electronegativity. For example, in peroxides, if you look at the oxygen's electronegativity, it is bonded with the hydrogen. Okay, now hydrogen's maximum oxidation number is +1. So there are two hydrogen. So two hydrogen will show +2. So therefore two oxygen will show -2. So if the two oxygen shows -1, single oxygen will show -1. So that is the oxidation state of oxygen in peroxides. And there are different types of peroxide. This is not the only peroxide. Oxygen has H2O2, then Na2O2, then O2F2. All of these are peroxides. Whenever you have something like O2, 2 minus, it is called as peroxide. Whenever you have O2, 1 minus, It is called as superoxide. Whenever you have single O, 2 minus, that is your normal oxide. This is your normal oxide where oxygen exists in this way. Okay, that is going to be always. But you should remember the peroxide and superoxide term also. Superoxide, KO2. Now in KO2, you have a potassium. Now potassium is a alkali metal, and alkali metals oxidation state is always +1. So if it is +1, the two oxygen will share a -1 charge. So if the two oxygen shares the -1 charge, we always talk about oxidation state of a single atom. So -1 divided by 2. That is why it is -1/2. That is what the oxidation state of oxygen in superoxide. Then ozonide, KO3. Again in KO3, you got potassium there. As I just told you, potassium stays in +1. That means O3 must have a -1. Why I'm immediately saying this? Because there is a charge on compound. And whatever charge you have for one atom, the same charge should be possessed by the other elements. Only sign is opposite, right? Because the overall charge is 0, no? So if the potassium is in +1, O3 has to be in the -1 because the overall charge of your compound is +1 -1, it is 0, right? So -1 charge is shared by 3 oxygen atoms, and therefore each oxygen atom's charge is -1/3. And lastly, oxygen with the fluorine. So as I told you earlier, fluorine is the most electronegative element. With the fluorine, oxygen also goes to the positive oxidation state because oxygen is a queen. You can say it's a queen of electronegativity, because if the fluorine's electronegativity is 4.00, oxygen's electronegativity is 3.50. Oxygen is the second most electronegative element of the periodic table. So in OF2, you got 2 fluorine. Each fluorine is in -1, right? As I told you earlier here. So 2 fluorine is in -2. Then oxygen has to be in a +2. And in O2F2, there are 2 fluorine atoms. Each fluorine atom is in -1. 2 fluorine atom is in -2. So 2 oxygen atoms are in +2. And therefore, each oxygen atom is in a +1. So basically, your oxygen shows -1, -2, 0, then +1, +2. If you're not talking about a fractional oxidation state, these are all the oxidation state shown by the oxygen. Okay, that is how the oxidation number are for oxygen and fluorine atom. Okay, so moving ahead, hydrogen atom. Now for the hydrogen atom, see, in general, hydrogen atom has oxidation number equal to +1. But when it will be +1 when it is attached to, whenever it is attached to more electronegative element. Whenever your hydrogen is attached to more electronegative element, its oxidation state would be +1. But in metallic hydrides, the hydrogen's oxidation number has to be -1, because see, hydrogen, you might have seen in the periodic table that hydrogen is kept just above the alkali metals. But in reality, that is not a real position of hydrogen, because hydrogen's electronegativity is 2.43. And if you look at the carbon's electronegativity, it is 2.50. So it is very close to carbon. And by that sense, it has to be p block element or non-metal. And why not so? Hydrogen shows the properties of s block element also, p block element also. It also shows the properties of d block element and a block element. By that all sense, hydrogen shows the elements of all corners in the periodic table. Okay. But anyways, that is not our point here. We will talk about that in a chapter called hydrogen atom. But for the time being, hydrogen's electronegativity is similar to electronegativity of other non-metals. That is why whenever hydrogen is attached to metals like sodium and potassium metals, their electronegativity lies somewhere around 1. It lies around 1, 1.1. Now that 1 or 1.1 is quite less than 2.4. This difference of electronegativity of 0.3 or zero point 0.4 is quite, 1.3 or 1.4 is quite large. It is enough to make or to create -1 charge on the hydrogen. That is why it is called as hydrides, IDE. This IDE stands for negative charge. Okay, so remember this thing. Whenever a hydrogen is attached to the metals, it is having a -1 charge. If it is attached with the non-metals, which are more electronegative than it, then it will have a +1 charge. These are the only two oxidation states shown by hydrogen. Then halogen atom. See, in general, fluorine, bromine, iodine has oxidation number equal to -1. Now here we are not talking about fluorine because we have already talked about it, right? So we are talking about the other halogen atoms. So other halogen atoms are chlorine, bromine, iodine. All of them has oxidation number equal to -1. Now if the halogen atom is attached to more electronegative element than themselves, for example oxygen, then they might show positive oxidation state. For example, in KClO3, oxidation state of chlorine is +5, iodine is a +5, chlorine is a +7 here, and bromine is a +5 here. Why? Because all of them are attached to oxygen, and oxygen is more electronegative than all the halogens except for the fluorine atom. That is why you will see all these halogens are in a positive oxidation state with the oxygen. Okay, sure. Moving ahead with this, metals. Let's talk about the oxidation number of metals. Alkali metals. Alkali metals, for example, lithium, sodium, potassium, rubidium, cesium, and francium. They always have oxidation number equal to +1. You will never see them having any other oxidation state than +1. Why? Why? Because if you talk about the alkali metals, general electronic configuration, their general electronic configuration is they have a noble gas core, and to outside it they have NS1. Now this N is 2 for lithium, for sodium N is equal to 3, for potassium N is equal to 4, for rubidium N is equal to 5, for cesium N is equal to 6, and for francium N is equal to 7. That means every alkali metal has one extra electron outside the noble gas core. Now see, noble gas core, having a noble gas core is a sign of stability, and that is why every alkali metal tends to lose this electron. Every alkali metal tends to lose this single electron to become a +1 cation, and in the process it gains the oxidation number +1. That is why alkali metal has the only oxidation number which is +1. Secondly, alkaline earth metal. Alkaline earth metals are what? Beryllium, magnesium, calcium. Then you have a strontium, barium, and radium. Now all of them are oxidation number +2. Why? Because they are the neighbors of alkali metals on the right hand side, and they have 2 electrons outside the noble gas core. So they can lose these 2 electrons to achieve this noble gas electronic configuration, and in the process they will acquire oxidation number of +2. That is why they always show +2 oxidation number. See, metals might have negative or 0 oxidation number. Now, I don't need to tell you that metals can have a 0 oxidation number because that is the oxidation number shown by every other element. Okay, but metal can show negative oxidation number also. Okay, we will see when the numerical or the example comes from that reference. Aluminium. Aluminium always have +3 oxidation number. Remember this point. Aluminium do not show any other oxidation number other than +3. Okay. Next, oxidation number of an element in a free state. Free state means what? Uncombined state, right? Oxidation number of any element in a free state or allotropic forms is always 0. So O2 is the allotrope of oxygen along with O3. Acid is allotrope of sulfur. P4 is the allotrope of phosphorus. Again, the O3 is the allotrope of oxygen. In all these elements, in all this molecule, these atoms are attached with the other atoms of same element. So that means electronegativity difference between them is 0. So if the electronegativity difference is 0, obviously there would not be any drifting of electron density away or towards, because of which their oxidation number has to be 0. Okay. So now, moving ahead, some helpful rules for you. What are these helpful rules? See, the sum of the charges of all the elements, sum of the charges of all the elements in a molecule is 0. It is always 0. That means, suppose if you have H2O, now in H2O, hydrogen has +1. There are 2 hydrogens, so together it becomes +2. Oxygen is having a -2, so +2 -2 it becomes 0. Similarly for the NH3. In NH3 there are 3 hydrogen atoms. Each one is in +1. +1 into 3 +3. Nitrogen -3. Total 0. The sum of charges of all the elements in a molecule is always 0, or the sum of charges of all the elements in an ion. Now here I was talking about molecule. Here I am talking about ion. That is why the sum of the charges of all the elements in ion is equal to the charge on the ion. For example, if I have a molecule like SO4 2-, the sulfate is minus. If you look at the oxidation number here, the oxidation state of sulfur is a +6. And you got 4 oxygen. Each oxygen is in what? -2. -2 into 8, -8. So 6 minus 8 is equal to -2. And that's the charge you have over the sulfate molecule. And that is why, or that is how, the sum of charges of all the elements in a given ion, an ion could be cation, it could be anion, is always equal to charge on that ion. Last, an important rule: if the group number of an element in periodic table is n, if the group number of an element in a periodic table is n, then its oxidation number may vary from n to n minus 8. N to n minus 8. Now this thing is mainly applicable in a p block element. This is mainly applicable in a p block elements. For example, nitrogen atom belongs to the 5th group. Okay, so your n is equal to 5 here. So what they're showing, or what they're saying, it shows the oxidation state from n to n minus 8. That means 5 has to be there, 5 to n minus 8. Now n minus 8 means here 5 minus 8. 5 minus 8 is equal to -3. That means they are saying nitrogen shows oxidation state from -3 to +5. And it really does show all those oxidation states. Let me show you how. See, NH3, nitrogen's oxidation state is -2. sorry, not minus 2, minus 3. It is minus 3 in ammonia. In N2H4, you got 4 hydrogen, no? So 4 hydrogen will have plus 4. So 2 nitrogen will have minus 4. And each nitrogen will have a minus 2. So minus 3, minus 2. Then you have a NH2OH, ammonium hydroxide, where your, sorry, not ammonium hydroxide, hydroxylamine, where your nitrogen is in minus 1. Then you have a N2 gas, which is 0. Now 0 is always there, you know that. So minus 3, minus 2, minus 1, 0. Let's see where it is plus 1. In N2O, 1 oxygen is minus 2. So 2 nitrogen is plus 2. Each nitrogen is plus 1. So here it is plus 1. Then you have NO, nitrosyl oxide, where nitrogen is in a plus 2. Then you have N2O3, where nitrogen is in a plus 3. Then you have N2O4, where nitrogen is in a plus 4. Then you have N2O5, where nitrogen is in a plus 5, or HNO3 also, where nitrogen is in a plus 5. So these are some of the oxidation states of nitrogen, where it shows the oxidation states ranging from minus 3 to plus 5. And I showed you how these rules can be helpful to you. Similarly, if you look at the oxygens, oxygen's group number is 6. Oxygen can show oxidation state from minus 2 to 6. Now remember, this rule is applicable to nitrogen only. I mean, if you look at the second period, from the second period, it is applicable only to the nitrogen. Oxygen is in the same period as nitrogen, but it is not applicable to oxygen, nor it is applicable to fluorine. But if you go to the next period, which is having a phosphorus or sulfur in it, for them it is exactly applicable. For example, sulfur. Sulfur is belonging to the oxygen, which is group 6. So according to our rule, it should show oxidation state from N to N minus 8. So N is 6, N minus 8 is what? 6 minus 8 minus 2. So sulfur should show oxidation state ranging from minus 2 to plus 6. And yes, sulfur does show those many oxidation states. Okay, we will explore it more and more as we will progress ahead. Okay, so moving ahead. Now, calculation of average oxidation number. Let's find out how we can calculate the oxidation number. First of all, what they have asked us, calculate the oxidation number of underlying element. Underlying element is what? Sulfur. How can we do that? See, you got Na2, S2, O3. Now, sodium is a alkali metal. We had seen that its oxidation state is always plus 1. You got 2 sodium, right? So plus 1 into 2. We don't know what's the oxidation state of sulfur, but there are 2 sulfur atoms. So we will write 2x, right? Then you got 3 oxygen atoms. Each oxygen atom is having a minus 2. Minus 2 into 3 is equal to charge. What is charge? Do you see any charge here? No, right? That means charge has to be 0. So you get 2 here. 2 plus 2x minus 6 is equal to 0. Therefore, 2x, 2 minus 6 minus 4 is equal to 0. Therefore, 2x is equal to 4 and x is equal to plus 2. So that is the oxidation state of your sulfur. Now the question is, does both the sulfur has plus 2 oxidation state, or does each sulfur has or is it the way that one sulfur is in a plus 4 and other is in 0? Because we are talking about the average. I'm talking about the average oxidation number. So let me tell you by drawing the structure whether really both the sulfur are in plus 2 or not. Let's look at here. S double bond S double bond O O minus Na plus, O minus Na plus. That's how the structure of Na2H2O3. So you can look at this. This sulfur is attached to this another sulfur only. That means oxidation number of this sulfur is 0. And if you look at this sulfur has formed 4 bonds with oxygen atom. Now whatever number of bonds you form with a more electronegative atom, that will be your oxidation number in positive. So sulfur has formed 4 bonds with the oxygen. That is why this sulfur's oxidation number is plus 4. So this sulfur is in plus 4, that sulfur is in 0. So if you take the average of both of this, it has to be plus 2. And that is how you have a plus 2 as an average. Okay. Next, here they have asked us to find out the oxidation number of this sulfur. Again, so we can solve it in the similar fashion. There are 2 sodium, right? So that means plus 1 into 2 plus 4 sulfur, therefore 4x. 6 oxygen, therefore minus 2 into 6 is equal to 0. Plus 2 plus 4x. 6 into minus 2 minus 12, 0. 4x minus 10 is equal to 0. 4x is equal to 10. And therefore x is equal to 2.5. So each sulfur is having a 2.5 oxidation number here. Now let me tell you, oxidation number generally is not present in a fractional number. Well, it may present in a fractional number, okay, but those cases are very rare. So now question is all the 4 sulfur atoms are in a 2.5 oxidation number or not? Let's find it out. How they actually are. See, S double bond O double bond O minus Na plus. Then you have a sulfur double bond O minus Na plus. So if you look at this sulfur, left side wala sulfur has formed 5 bonds with the 5 oxygen, 5 bonds with the oxygen atom. That means its oxidation number is plus 5. And this sulfur is attached to sulfur from both the side. Same is the case with this sulfur. So both of this shows 0 oxidation number, and this sulfur shows plus 5 oxidation state, just like this one, because it also has formed 5 bonds with the oxygen atom. So plus 5, 0 plus 0 plus 5 is equal to 10. 10 divided by 4 is equal to 2.5. That is how you have average oxidation number 2.5. But it sometimes might mislead you. You had seen already in both these cases. Okay. So moving ahead. We have to find out the oxidation number of all the atoms here. First is ClO minus. Now we don't know what's the oxidation number of chlorine, right? So again we'll write the X. For oxygen it is minus 2. What is it? Is equal to overall charge. Overall charge is not 0 here, it's minus 1. So X is equal to minus 1 plus 2. Therefore X is equal to plus 1. That is why chlorine has plus 1 oxidation number here. Now NO2 1 minus. Again nitrogen X, 2 oxygen minus 2 into 2 is equal to minus 1. So X minus 4 is equal to minus 1. X is equal to minus 1 plus 4. 4 minus 1, 3. X is equal to plus 3. So plus 3 is the oxidation state of your nitrogen here. Then NO3 1 minus. Nitrogen again X, 3 oxygen minus 2 into 3 is equal to minus 1. So X minus 6 is equal to minus 1. X is equal to minus 1 plus 6. X is equal to plus 5. That's the oxidation state of nitrogen in a nitro group. Then you have a CCl4. Now carbon's oxidation state we don't know. So X. Each chlorine is in a -1. So you got 4 chlorine atoms. So -4 is equal to 0. And therefore X is equal to +4. So carbon's oxidation state is +4. Then you have a K2CrO4. Here you need to find out for the chromium. Here you need to find out for the manganese. K2CrO4. CrO or Cr2? Yeah, CrO4. So again, potassium is in a +1. So you have +1 into 2. Then plus chromium. Again X. 4 oxygen -2 into 4. Overall charge is 0. So +2 plus X -8 is equal to 0. 2 minus 8 is X -6 is equal to 0. Therefore, X is equal to +6. That is the oxidation state for the chromium. Then next you have KMnO4. Here again for potassium +1, manganese X, 4 oxygen -2 into 4. What is the charge? 0 again. So 1 plus X -8 is equal to 0. X -7 is equal to 0. Therefore, X is equal to +7. That is how you can find out the oxidation states. That is the way. Okay. So, moving ahead. Some miscellaneous examples. Now, CrO5. You can find out the blue colored element here, chromium. So they have asked us to find out the oxidation number of chromium. The question is it the way or is it the oxidation state you are going to get? For example, look at this. Let's find it out. X plus -2 into 5 is equal to 0. So X -10 is equal to 0. Therefore, X is equal to +10. So it appears that chromium has oxidation state on number 10, +10. But that is not the case. That is simply not possible because the highest oxidation state, shown by any element is +8. You cannot go beyond +10. And it is also, this +8 is shown by rhenium and osmium. These are the only two elements which shows +8 oxidation state. No other element shows this higher oxidation state. Okay. So that means oxidation state of chromium is not +10. Then what is the catch here? See, let me show you what is the catch. For this, you should know the structure. Now, this is obviously an exception. The structure of CrO5 is this. Oxygen, oxygen. Then you have oxygen here, like this. CrO5. See, that is how the CrO5 actually looks like. You can see here the chromium has formed a 6 bonds only, which makes oxidation state of chromium +6 only, and it is +6. This structure, you can see it appears like a butterfly. That is why it is called as a butterfly structure. It is called as butterfly structure. Same H2SO5. Again, if you find out the oxidation state of sulfur here, it is +1 into 2, +2 for hydrogen, sulfur X, for oxygen -2 into 5, 0. So +2 plus X -10, 0. X -8 is equal to 0. Therefore, X is equal to +8. So as I told you, +8 oxidation state is possible, but it is not possible for the sulfur. Why? Now you should also know what are the oxidation state can be shown by given element. We had seen earlier that sulfur can show oxidation state from -2 to 6 only. Okay. Now we will see what is the reason behind it. Say if you write the sulfur's electronic configuration, the atomic number of sulfur is 16. So its electronic configuration is neon 3s2 3p4. So these are the 6 electrons sulfur has outside this noble gas core, which is neon. So sulfur can show maximum oxidation state of +6, and it can gain 2 electron to become argon. So when it gains 2 electron, it becomes -2. That's the reason sulfur shows oxidation states ranging from -2 to +6. That means this +8 is not right, and that means there must be some catch. And what is that catch? The catch you will come to know when I'll draw the structure. The structure of H2SO5 is S double bond O, S double bond O, O, OH, and OH on this side. So this is peroxymonosulfuric acid. You know that H2SO4 is called as sulfuric acid only. You know that, right? We already know that right from our childhood. It's a king of an acid. So H2SO4, this is H2SO5. So you got one oxygen atom extra. And that oxygen atom is present as peroxide linkage. You can look at here. This is peroxide linkage. And that is why H2SO5 is called as peroxymonosulfuric acid. And if you look at the sulfur here, sulfur has formed 6 bonds with the oxygen atom, which makes sulfur's oxidation state to be +6, and it is +6. This +8 is wrong. These are some of the exceptions, or I would say miscellaneous example, where we had seen that actual oxidation state is different than what we can calculate or than what it seems to be. Okay, sure. Next, paradox of fractional oxidation states. What is this paradox of fractional oxidation states? See, C3O2. If you find out the oxidation state of C3O2 here, you got 3 carbon, so 3x, 2 oxygen, each oxygen is in -2, so 3x minus 4 is equal to 0. Therefore, 3x is equal to 4, and therefore x is equal to 4/3. Or you can say 1.33. So that is the fractional oxidation state possessed by a single carbon atom. But the question is it so? Question is it so? No, it is not so. The real structure of compound is this: C double bond C, double bond C, double bond O, double bond. This is also called as carbon sesquioxide. It is also called as carbon sesquioxide. So you can see this carbon is in a +2. This carbon is in a +2. Together they contributes the +4, and this carbon's oxidation state is 0. And that is why we take the average of all this, which comes out to be +1.33. Okay, same is the case with the Br3O8. Here also, if you look at the bromium, the oxidation state of bromium has to be 3x minus 16, 0. Therefore, 3x is equal to 16, and therefore x is equal to 16/3, which makes it something like 5.33, something like that. 5.33. But again, is it the 5.3? Is it like that? Is each bromine has the same oxidation state which I had shown here? Let's see. Let's see how its structure actually is. So, the structure actually is like this: double bond O, double bond O, double bond O. Then you have a bromine here, another bromine, double bond O, double bond O, double bond O, this double bond O, and double bond. That's how the structure is. So this bromine, it has formed 6 bonds with the oxygen atom, and from the another side, it is bonded singly with the another bromine. So from that side, there is no contribution, but from the other side, it is bonded with the oxygen atoms, has formed 6 bonds. Therefore, bromine is in a +6 here. This bromine on the similar line has +6, and this bromine has formed 4 bonds with the oxygen atom. This bromine is in a +4. So 6 plus 6, 12, plus 4, 16. So that is how +16 charge has been distributed among 3 bromine atoms. Okay. Next is S4O6 2-. We had already seen its structure, but that time in that case we had seen it with the sodium. This time there is no sodium here. It is S4O6 2-, right? So each sulfur is in a +2.5 here, and we had seen it. Its structure is like this: S double bond O, double bond O, O-, S S S double bond O, double bond O, and minus. So this sulfur is in a +5, this sulfur is in a +5, and both these sulfurs are in 0 oxidations. So that's how you get 5 plus 5, 10 plus 0, and 10 divided by 4, 2.5. So that is how the paradox of fractional oxidation state is all about. Okay, moving ahead. Oxidizing and reducing agent. What is oxidizing agent? The oxidizing agents are those compounds which can oxidize others. Oxidizing agents are those compounds which can oxidize others and themselves getting reduced. Now this is obvious. If I'm giving you something, I will lose something. So it's just like that. So if I'm oxidizing you, I have to get reduced. So oxidizing agents are those compounds which can oxidize others and themselves getting reduced during chemical reaction. So since they are oxidizing other, that means they are forcing other compound to lose electron. And since they are getting reduced themselves, that means they are gaining the electrons. That is why these reagents oxidation number decreases, because they are getting reduced. No, that is why their oxidation number decreases or they gains the electron. Now again, obviously we are putting the same thing in a different word. If they are getting reduced, they have to gain electron and they have to decrease their oxidation number also. So such a species are called as oxidant or oxidizing agents. Okay. What are some of the stronger oxidizing agents? The most prime examples are KMnO4, K2Cr2O7. These are the most important oxidizing agents which are used in a different organic reactions. Okay, KMnO4 and K2Cr2O7. HNO3, nitric acid, it is also a good oxidizing agent. Lastly, concentrated H2SO4. Concentrated H2SO4, these four are the powerful oxidizing agents. Now, if these are the oxidizing agent, what must be your reducing agent? Something which is exactly opposite to this. Exactly opposite to this. What is it? Reducing agents are those compounds which can reduce others. Now, oxidizing agents was oxidizing others. So, what reducing agent will do? Reducing agents are those compounds which can reduce others and oxidize itself. They themselves getting oxidized. See, this will always be the thing. If you are reducing someone, you will get oxidized. If you are oxidizing some another agent, you will get reduced. The reducing agents are those compounds which can reduce others and oxidize itself during chemical reaction. Now, obviously, if you are getting oxidized, your oxidation number has to increase or you should lose electron. Again, we are putting this in a different words. We had seen these definitions already. So those reagents whose oxidation number increases or which loses electron in a redox reaction are called as reductant. Now, what are some of the powerful reducing agents? the Ki, Na2H2O3, sodium not thiosulfate actually, sodium thiosulfate, yes, sodium thiosulfate, and potassium iodide, and Hi. These are some of the powerful reducing agents. We will see their use as we progress ahead. There are some compounds also which can work both oxidizing as well as reducing agent. There are some compounds which can act for oxidizing as well as reducing agent. What are those? H2O2. Hydrogen peroxide is one of them, and another is NO2 1 minus, nitro group. Nitro group and hydrogen peroxide are the compounds which can act as oxidizing as well as reducing agent. Okay. Now how can we come to know whether given atom or given species is oxidizing agent or reducing agent? How can we do that? See, first find the OS. OS means oxidation state. Okay. Now this abbreviation we will use quite oftenly. We'll either use OS or we'll use the ON. Okay. OS stands for oxidation number. OS stands for oxidation state. Okay. Both are one and the same thing. Okay. So find the OS of a central atom. Then if that oxidation state is its maximum oxidation state, if that oxidation state is its maximum oxidation state, then it has to be oxidizing agent. For example, H2SO4. Now in H2SO4, sulfur's oxidation state is +6. Now +6 is sulfur's highest oxidation state. From this oxidation state, sulfur cannot get oxidized itself. Now sulfur can only get reduced. If sulfur can only get reduced, that means sulfur can act as a oxidizing agent. And that is why, and that is how H2SO4 can act as a oxidizing agent. Secondly, if the OS of a central atom is minimum OS, if whatever oxidation state your central atom has, if that oxidation state is its minimum oxidation state, then it can act as a reducing agent. For example, Hi. In Hi, now hydrogen do not act as an oxidizing or reducing agent as such. So let's omit the hydrogen. Look at the iodine. The oxidation state of iodine here is -1. Now -1 is iodine's minimum oxidation state. So iodine cannot go beyond -1. That means iodine cannot become -2 or -3. So that means from -1, it can only become a 0, or it can only go to +1, +2. And in doing so, it will only get oxidized. If it only get oxidized in that way, that means it can act as a reducing agent. And that is how Hi can act as a reducing agent. And lastly, now this point is somewhere in between both these two extremes. If the oxidation state of a central atom is in between, then it can act both as oxidizing agent as well as reducing agent, or it can disproportionate also. It can disproportionate also. Now how and why it can disproportionate, that we will see in the next lecture. Okay, but for the time being, if the maximum oxidation state is achieved by the central element, it's oxidizing agent. If the minimum oxidation state is possessed by central element, it can act as a reducing agent. If it is in between, it can act as a both, or it can disproportionate. Okay, so moving ahead. Now redox reaction. Now we come to the name of our chapter, because other terms that we had seen till now, which is oxidation number, reduction number, then how to find them out, oxidizing agent, reducing agent, all of these are important in a redox reaction, because if you understand them, then only you can understand what is redox reaction. So it is a reaction in which oxidation and reduction takes place simultaneously. It is a reaction in which both oxidation and reduction takes place simultaneously. In all redox reactions, the total increase in oxidation number, in all redox reaction, the total increase in oxidation number must be equal to the total decrease in oxidation number. That means the number of electrons lost should always be equal to number of electrons gained. Okay, that is the case always in a redox reaction. You will see that quite often. Let me give you a demonstration for it. Look at this FeSO4. In FeSO4, the charge on sulfate is -2 always. So if the sulfate has -2 charge, the ion will have a +2 charge. Okay? So oxidation state of ion is +2 here. If you look at this Fe2SO4 3, the charge on sulfur again is -2. The charge on 3 sulfur is -6. Charge on 2 oxygen at ion atoms is +6. Each ion atom is +3. So basically your ion has come from +2 to +3. So each ion atom has come from Fe +2 to Fe +3. And how many total Fe atoms we have? Total 10. That means loss of electrons here, that means loss of electrons here is 10. Is of 10 electrons. Let's look at the gain in electron. Now look at the manganese. The oxidation state of manganese here is how much? It's a +7. It's +7. And the oxidation state of manganese here again manganese is with the sulfate, right? So if the sulfate is in a -2, manganese has to be in the +2. So each manganese atom has come from +7 to +2. Each manganese atom has come from +7 to +2. That means each manganese atom has gained 5 electrons. And how many manganese atoms are there? 2. And therefore, total gain of electrons is also 10. So you can look at here, the loss of electron and gain of electron is exactly equal. That means reaction is balanced also, and it is a redox reaction. That is how you can find out whether given reaction is redox reaction or not. That is a way. Okay. Now let's see some of the numericals. Oxidation number. The incorrect order of decreasing oxidation number of sulfur in a given compound is. Now that order is incorrect or not. For that we need to find out the oxidation states of sulfur first. So in H2S2O7, let me tell you how to calculate it orally. See, oxygen is in -2, -2 into 7 -14, 2 hydrogen, so -14 plus 2, because hydrogen is in a +1, right? So -14 plus 2, it is -12. So apart from sulfur, others are present in +12. That means sulfur must be present in a +12. So 2 sulfur in a +12. That means each sulfur is in a +6. Then here 6 into 2 -12, -12 plus 2, 10. 10 divided by 4 plus 2.5. Then here 3 into 2 6, 6 -6 plus 2 plus 4 plus 4 divided by 2 plus 2. And X set is an allotrope of sulfur. So this is 0. So this order is correct, right? This order is correct. You're going from 6 plus 6 to plus 2.5 to plus 2 and 0. They have asked us to find out the incorrect order, right? So let's go here. Here we had seen this case already, right? Here the sulfur was in a +6 oxidation state. Remember, peroxymonosulfuric acid. Yeah, +6. In H2SO3, 3 into 2 -6, minus 6 plus 2 minus 4. So sulfur is in a plus 4. So plus 6 is larger than plus 4. That is right. Then you have HCl2. In HCl2 it is in a plus 2. And in H2S it is in a minus 2. So plus 6 plus 4 plus 2 minus 2. That means this order is also correct. Going to the last. In SO3, 3 oxygen, that means minus 6. Then sulfur has to be in a plus 6. SO2, 2 oxygen minus 2 into 2 minus 4. Sulfur has to be in a plus 4. In H2S, it is in a minus 2. And in acid, it is 0. So this order is incorrect. After plus 6 plus 4, you can have 0, then you have a minus 2. You cannot have minus 2 larger than 0 because minus 2 is smaller than 0. That is why this order is incorrect. And lastly, in which of the following reaction is there change in oxidation number of nitrogen atoms? So for this, you need to check all the elements oxidation state, whether it is changing or not. See, in NO2, nitrogen's oxidation number is plus 4. In N2O4, also it is plus 4. So there is no change in OS here. Next, here. In NH3, nitrogen's oxidation state is minus 3. Sorry. It is minus 3 here. Array, what is happening here? Oh shit. Yeah. So here it is minus 3. Now let's see what is oxidation state of nitrogen in NH4 plus. In NH4 plus, nitrogen's oxidation state we don't know. X. You got 4 hydrogen. Each hydrogen is in a plus 1, right? So you got plus 4 is equal to total charge plus 1. So X is equal to 1 minus 4. X is equal to minus 3. So your nitrogen here also is in a minus 3. So there is no change. Lastly, N2O5. In N2O5, nitrogen is in a plus 5. We had solved it earlier. And in H1O3 also, it is in a plus 5. So change in oxidation number is happening in no case. And that is why the answer is no. That is how you can solve the oxidation number. That is how you can find out the oxidation number, and that is how you can solve the numerical or question based on it. And that's it for today. We have covered the primary part of this chapter. In the next lecture, we will cover how to balance the chemical equation by using this oxidation number and how to balance them. We will see that in the next lecture. Okay, that's it for today. Bye bye everyone.